So there are pretty much two reasons why we might care about concavity in terms of applications. Two specific things that this can apply to. But in general, concavity, talks about concave up, concave down, but inflection points are where the concavity changes, just like we were talking about before. So the inflection point, and you'll remember this from the notes that we discussed about the properties of inflection points. So the inflection point is where the rate of change is the largest. So this is where the graph is the steepest. So this is where the rate of change is the largest. In other words, graph is the steepest because rate of change is the derivative, which is the slope. And if you have the largest slope, that's pretty steep. So this is useful in applications. Okay, so in two specific cases, one of them is in population growth. So normally functions that model population growth look like this. Okay, so you've got on the x-axis or the horizontal axis, we've got maybe time. And then on the vertical axis, we've got population. Okay, so this function is modeling population over time. So it starts off kind of slow. There's like a lot of members in the population that are reproducing quickly. So it starts off growing pretty quick. And then there's like some kind of carrying capacity that the environment can sustain. So it starts to level off. So I guess we can start right about here is an inflection point. Okay, it's concave down to the left, and it's not right. I don't know what's wrong with me today. I keep switching these. I'm sorry. So it's concave up to the left and concave down to the right. That looks better. Okay, and the inflection point, this is where the population is growing the fastest. Okay, and then right at that point, like right after, is where it's still growing. It's just not growing as quickly. Okay, so the inflection point is interesting to find. And if you're interested in applications, which of course you are, in this specific context. Another example is point of diminishing returns. So this is an economics application. So if you have some kind of function, that is not a great graph, that models money spent on something. So we'll just say this is money spent. Or costs. And then typically on the y-axis, this would be the sales. Then the inflection point is right here-ish, right? It's concave up, got it right that time, concave down. Okay, here's the inflection point. And this is where the graph is the steepest. But in terms of like economics, if you've got this on your input is like costs spent, like money spent, maybe we'll look at an example in a second on advertising, then your sales are increasing still. If you spend more money on advertising, say, your sales increase until about here. But after this inflection point, the more you spend, the less you get back. So there's a point, that's what's called diminishing returns. The more you spend, you're still increasing, but not as much of an increase as there used to be. Okay, so this is where the increase starts to decline. It's hard to think about, but when the increase in sales starts to decline. So spending a little more money on advertising, say, will still get you more sales, but it's not worth as much as it was once you reach a certain point. Okay, so here's a specific example with diminishing returns. We'll actually come back to this population growth example when we start talking about exponential functions, because then we can get a nice model. This is called a logistic function when we have this shape. So here's a diminishing returns example. By increasing its advertising costs X, which is measured in thousands of dollars, for a product, a company discovers that it can increase the sales Y in thousands of dollars. According to this model, Y equals -1/10 x to the third plus 6x squared plus 400. And this is only valid between 0 and 40 for x. We want to find the point of diminishing returns. Point of diminishing returns. So this is the inflection point. Okay, so we're going to take the derivative and then take it again. So let's say this will be -3/10 x squared plus 12x. The second derivative will be -6/10 times x plus 12. Or that'll be, we can divide 6 and 10 by 2, so that'll be -3/5x plus 12. Okay, we want to find where the second derivative is equal to 0. I'll make this a different colored. So let's say second derivative equals 0. So if we do -3/5x plus 12 and solve for x, so we'll do -3/5x equals -12. We'll multiply by -5/3. -12 times -5/3 is +20. Okay, so we do need to make sure though that the the sign of the second derivative changes at 20, because otherwise it's not going to be an inflection point. This is only good between 0 and 40, so we'll say 0 to 20 and then 20 to 40, right, just because of this up here. We want to test the sign of the second derivative, so let's do y double prime of, I don't know, how about 1? So when we plug a 1 into the second derivative here, -3/5 times 1 plus 12, that's a positive number. When we plug a, I don't know, how about a 21 into the second derivative, we get -3/5 times 21. I don't know what that is, -3/5 times 21. And then let's add 12 to that. And that comes out to be a negative number. So it actually does change concavity there. So this is indeed an inflection point. And so let's answer the question. The point of diminishing returns is when x equals 20. So this would be when they spend $20,000, because x is measured in thousands, on advertising. All right, in the next video, we will look at what is called the second derivative test. It's a really cool thing that we can do with the second derivative. So tune into that and I'll see you then.